In this lesson, we'll explore in more detail how deep learning algorithms are implemented. Specifically, we'll look at the basic building blocks for convolutional neural networks, CNNs. We will discuss how to train a neural network and then introduce various considerations on training, such as the learning rate, the need for momentum to avoid saddle points, and much more. What are convolutional neural networks, or CNNs? They are a specialized kind of neural network for processing data in a known grid-like spatial structure. This allows them to work really well on imaging applications. By comparison with more traditional machine learning solutions, deep networks, and CNNs in particular, are usually very deep, with lots of layers and having lots of weights. A quick reminder of what a fully connected neural network looks like. We have an input layer, one or more hidden layers, and an output layer. The dimensions of these layers can be anything, but typically for a classifier, we have one input per pixel in an image, and we go through a bottleneck of hidden layers to reduce to the number of classes in the output layer. In this diagram, each circle represents a neuron. As this is a fully connected network, each neuron takes a feed from all the inputs and multiplies each input by its own individual weight. Then it sums all these values up, potentially also adding a bias term. This final summed value is passed to an activation function, and the result of the activation function is output to the next layer. By comparison with fully connected networks, CNNs are typically comprised of a large number of layers of different types: convolutional layers, activation functions, pooling layers, and fully connected layers. With convolutional and pooling layers, the difference is that not all inputs are fed to each node in the next layer, i.e., it isn't fully connected. This imposes a spatial mapping. Nodes get inputs from nearby nodes in their input layer. This is known as the concept of a receptive field. Let's look at the various layer types in a typical CNN in more detail. Convolutions are similar to the edge detection kernels that we saw earlier with Hog. In CNNs, we convolve an input volume with a weights volume. In practice, this means we convolve, matrix multiply, a number of 2D weight planes across our input volume. We are using some wonderful animations from A Guide to Convolutional Arithmetic for Deep Learning to help us explain what convolution is. Blue maps are inputs and green maps are outputs. You can think of the darker blue overlaid on the blue inputs as the convolutional kernel weights. Here, we are taking a 3x3 convolutional kernel and striding it by one at a time across an input size of 4x4, generating an output of 2x2. Depending on our padding and our striding, we can take our input layer and shrink it or expand it purely with convolutional layers. For example, here we have a convolutional kernel of 3x3 striding with a stride of 2 across an input of 5x5 and using a padding of 1. This results in a 3x3 output. The thing to remember is that there are a number of these convolutions going on strided across the image, and we end up processing all the inputs in the input layer and converting them into an output layer, taking into account our striding and our padding. As we're doing this, we're often reducing the spatial width and height of the previous layer, but increasing the depth. We need our neural network model to learn and represent any arbitrary complex function, which maps inputs to outputs. In this manner, neural networks can be considered to be universal function approximators. They can learn any arbitrary function. Using a nonlinearity allows the network to learn more complicated functions that are not necessarily a linear combination of their inputs. So, if we want our network to learn more complicated functions, we need nonlinearities in our activation functions. Without a nonlinear activation function, the network would collapse to a single layer, because summing all these extra deep layers would just give another linear function. Sigmoid was a popular early activation function and is still commonly used in logistic regression. The sigmoid function asymptotes to 0 at minus infinity and to 1 at plus infinity. At 0, the sigmoid function outputs 0.5. Sigmoid has fallen out of favour as an activation function for a number of reasons. It is typically slow to converge, it saturates and kills gradients due to compression, and its output isn't zero-centred. We want to be able to have deeper networks if our problem needs it. Deeper networks have more capacity, and experiments have shown that more layers can significantly help with accuracy in certain applications. However, more layers means longer time to train, and potentially more compression or saturation on gradients with sigmoid. By compressing our range into 0 to 1, sigmoid can cause error gradients to vanish as they are back-propagated through the layers of our network. This slows down training and can kill gradients entirely, causing potential model accuracy loss. The hyperbolic tangent function is zero-centered, so optimization is easier. It asymptotes at -1 at minus infinity and at +1 at plus infinity. But it still suffers from vanishing gradients by compressing into a -1 to +1 range. The rectified linear unit activation function maps positive inputs to themselves and negative inputs to 0. It is faster to train and reduces the likelihood of a vanishing gradient. It also introduces some sparsity when the input is less than 0, which can help with regularization and overfitting. One point to note with ReLU is that it should only be used in the hidden layers. For output, it is more typical to use a softmax for classification to compute probabilities for classes, and a linear function for regression. ReLU would not give an accurate probability output, and so something that compresses to between 0 and 1 would work much better for output. Another problem with ReLU is that some gradients can be fragile. In these situations, leaky ReLU can often work better. Leaky ReLU is a variant of ReLU that maps positive inputs to themselves, but negative inputs to a small-scaled version of themselves. It doesn't compress as much. ReLU is probably the most popular activation function in convolutional networks today. A pooling layer provides a downsampling of the image, reducing the spatial size of it. They are used to reduce computational requirements, minimize likelihood of overfitting, and provide some degree of invariance to local translation, similar in some level to Hogg's cells. The most common methods are max pooling and average pooling. Let's take a look at both. Average pooling uses mean values within a window. In this case, it has added the values of all the input cells, shaded in dark blue, 12, divided by the number of cells, 9, and stored this value in the dark green cell in the output layer, approximately 1.3. Max pooling finds the largest value in the window. In the dark blue shaded area, we can see the largest value is 3 at the top right. This is the value max pooling will pick for its cell, shaded in dark green. Max pooling has demonstrated fast convergence and good performance, and it is commonly used. The final output of a CNN is often a fully connected layer or set of fully connected layers. These layers are used to arrive at a final probability distribution for the class of an image. In a dense layer, each input is connected to every output by weight, like our example at the start of this video. As we mentioned, ReLU is usually used only for non-linearities in our hidden layers, and we use a softmax at the final output to calculate probabilities. Softmax takes each input, passes it through the natural exponential function, and divides the result by the sum of all inputs passed through that natural exponential. This will make more sense with an example. Here we have 3 possibilities for z. Next, we raise e to the power of that input. So e to the power of 1.4 is approximately 4.1. E to the power of 0.7 is approximately 2.0. Then we sum all of these results across all of our inputs, and we get 7.9. Finally, we divide each exponential by our sum to get our softmax output. So our softmax output for an input of 1.4 is 4.1 divided by 7.9, which equals approximately 0.5, and so on. Now, if you look closely at the column of softmax outputs, you'll see the total always equals to 1, as it is a probability distribution.